Hi friends, in this video let us learn about the channel length modulation of MOSFET. Right, so we know that the VDS versus ID curve, that is drain characteristics curve, for MOSFET is given like this. So if you don't know, please refer my video on current voltage characteristics of MOSFET. Right, so ideally the curve should be like this. Here it is a saturation point, so VDS sat. Right, so the region before this one is called triode or linear region. After this it is saturation region. Okay, when VDS is greater than VDS sat, then MOSFET, and you see VDS, when VDS is greater than VDS sat, the MOSFET will enter into saturation region. Right, so these are all saturation region in this side. Okay, you see what is the slope? Here slope is dy by dx. What is y-axis? dID by x-axis dx dds. So you see, in ideal condition, what is the slope? When VDS increases, ID remains constant. So change in ID is 0. So slope is 0, ideally. But what happens is, in practice, it won't be like this. So the curve goes to here, the slope is not 0. Right, so slope is not 0, it has non-zero slope. Right, y changes something like that. So here in practice, di by dds not equal to 0. That is, slope is not equal to 0. Let us see what is the reason. The reason for that is channel length modulation. Right, so what is channel length modulation? It is nothing but reduction in channel length, for VDS greater than VDS sat in saturation region. Right, so this phenomena is called channel length modulation. Okay, so we know that when you apply some VDS in MOSFET, see, these are all already explained. Just for recalling purpose, I'm telling that. So let us take what is the thing? MOS oxide metal gate source drain. Right. So when you increase VDS, when you increase VDS value, that's what we have done here, right? So when we increase VDS value, the drain side will become more positive, right? So more positive means it is becoming more reverse bias because it is p-type body. This is p-type simulator. This is n plus n-type. You are giving p to n, so it will, drain side will become more reverse bias. So depletion region will become wider, and the channel starts reducing from the what you call drain side. So what happens if VDS increases? Channel length. So from initially, let us assume channel length will be like this. After some time, what happens? Channel length comes to this location because of increase in VDS. So when VDS increases, channel length decreases. This is called channel length modulation, right? So reduction in channel length, if VDS is greater than VDS sat in saturation region, is known as channel length modulation. When length decreases, what will happen to resistance? Resistance will decrease because R is equal to rho L by A. So when length decreases, resistance decreases. Clear? So when resistance decreases, what happens to current? Current will increase. Right? So this is a point we have to remember. So in saturation region, due to the channel length modulation, we are having current equation like this. We know for without channel length modulation, we have already derived current equation. It is K into VGS minus VT squared in saturation region. Now we have invoked a new parameter, channel length modulation. Because of the channel length modulation that we have to include, it is lambda V. So here lambda is channel length modulation parameter. Channel length modulation parameter. Right? So you see, due to this lambda, because of lambda, ID increases because 1 plus something is greater than this parameter, because this is already we know ID is equal to K into VGS minus VT square. It is without channel length modulation. So let us take this capital ID means capital ID into some parameter which is greater than 1 means ID will be greater than capital ID. So because of lambda, ID increases. That's what we have told, that we have proved already. Right? When channel length due to the channel length modulation, drain current will increase. Okay, now we will go to the ideal curve. You see, this is let us extrapolate this and extend this curve. Let us assume this curve meets this point at some location. Here VD is equal to what? 0. So let us assume this is minus VA. Right? So at this point, what is ID value? We will find. Okay, so you see, ideally it is 0, but we know ID is equal to K into VGS minus VT squared into 1 plus lambda VDS. So you see, at this point ID is equal to 0, right? At VA, when VD is equal to minus VA, ID equal to 0, right? So substitute that. When VDS is equal to minus VA, ID equal to 0. Substitute here. So this implies 0. You see, because of this point, these are all constant. These parameters cannot make ID equal to 0. Only this one can make ID is equal to 0 because this is constant, this is constant, and this is also constant. So this value cannot be changed. But this is fixed value. For every operation, this is fixed. VT is fixed. So lambda VDS only will change. So ID will be 0 because of this parameter. So 1 plus lambda VDS is minus VA. At that time only it is 0. So this implies VA is equal to 1 by lambda. What is VA and all? We will deal it in detail in small signal model. It is called the early voltage. Right? So that is a pointer. Okay. Now we know ID. We define new parameter, that is RO. Right? So RO is resistance, output resistance due to channel length modulation. Right? So we know in ideal condition R is equal to 0. What is the reason? You see, ID by VGS, right? Sorry, ideal condition it is infinity. Change it. You see what is dID by dVD is 0. I by V. I by V, if you take, it is 1 by dVDS by dID. That means what? Infinity. Then only it will become 0. Right? I write it. dID by dVDS as 1 by dVDS by dID. You see it is R. V by R. So this R is infinity means it is 0. So without the channel length modulation, we make R0 as infinity. So if no channel length modulation, R0 is infinity. But in practice, channel length modulation is there. At that time, what is R0 we are going to find. Right? So we know due to the channel length modulation, ID is given by K into VGS minus VT square into 1 plus lambda VDS. What is R0? I define R0 as dou ID by dou VDS inverse. That is 1 by dou VDS by dou ID. That's what I write. So if I differentiate ID with respect to VDS, what is R0? ID with respect to VDS, it is lambda only. So lambda K, right, into VGS minus VT square inverse, right? So this is given by, what is this factor? K into VGS minus VT, that is ID. So lambda ID inverse. This implies R naught is equal to 1 by lambda ID. This is output resistance due to channel length modulation. If lambda 0, R naught infinity. That's what we have proved already. Yes or no? If no channel length modulation, R naught is equal to infinity. That is mathematically proven now. Right? If lambda 0, R naught is equal to infinity. Right? Here we have proof. This is mathematical proof. This is graphical proof. Right? Okay. We know already what is lambda and VA relation. VA is equal to 1 by lambda. So I can write R naught is equal to VA by ID. You see, R is equal to V by I. Same Ohm's law satisfied. So in this way, we can understand channel length modulation. So these are all important parameters. What are the parameters we learned today? What is channel length modulation? Lambda. What is R naught? Output resistance due to channel length modulation. When it is infinity, when it is finite. R naught is equal to infinity if lambda is equal to 0. Right? It is finite when lambda is not equal to 0. Right? So these are all the things we must know in the channel length modulation process. If you have any doubt, please ask me in the comment section. I will clarify. Thank you.